My name is Adrian Morrison. I'm a research scientist here at Q-Chem, and it is my great pleasure today to introduce the speaker for today's truly very interesting webinar, Professor John Herbert. John got his bachelor's degree at Kansas State. He's a double major in chemistry and mathematics. He went to University of Wisconsin-Madison, where he did his PhD with John Harriman. After that, he did postdocs with Anne McCoy at Ohio State at the time, and also with Martin Head Gordon at UC Berkeley. He went on to join the Ohio State faculty in 2006 and acquired full professorship in 2014. Along the way, John acquired numerous honors and awards. There are too many to mention here. John has been a board member of Q-Chem since 2012 and is also a Q-Chem developer. His group contributes cutting-edge new quantum chemistry methods in areas like multi-layer, QM-MM methods, excited states and photochemistry, and many more. He has applied these methods into pretty wild systems such as the hydrated electron, and has also investigated vibronic singlet fission. Last but not least, John was my PhD advisor, and I thought he did a pretty awesome job. Again, please submit your questions in the little question box here on GoToMeeting, and here's John.
Thanks, Adrian. Cutting edge software. As I once heard someone say, you must be very careful with, else you hurt yourself. So I hope your experience with Q-Chem is more pleasant. So yeah, I will be giving the auspicious 28th Q-Chem webinar talking about new features in version 5.1. So the list, this is not a complete list of new features, but these are the ones that I will discuss today. So the first two are performance improvements, so better parallel scaling both for SCF vibrational frequencies and also for the RNP2 gradient. And then the next three are completely new features, so CAS-SCF, which you presumably are familiar with, and then a new version of that called adaptive sampling CI, some magnetic resonance parameters, including electron nuclear spin interactions, and then core-valence separation methods to calculate core to valence excitations using equation motion coupled cluster methods. And then the etc. is a couple of more specialized things that I'll tell you about very briefly. And then at the end, I will take some questions. Okay, so to start with multi-threaded or OpenMP vibrational frequencies at the SCF level of theory. So in Q-Chem 4, the only parallelism that was available for vibrational frequencies was an MPI-based parallel procedure that worked okay, but better for Hartree-Fock than for density functional theory. Starting with Q-Chem 5.0, the release a year ago, we had OpenMP parallel vibrational frequencies for the Hartree-Fock level, and now finally we have those both for Hartree-Fock and for DFT, but also with a number of performance improvements, including a BLAS-based dense matrix multiply-based exchange correlation kernel. So let's get right on to some data. So I'm going to show you 2 slides worth of data for this little molecule. These are frequency calculations. Omega B97X631G star. So this is a range separated hybrid functional. And there's sort of 3 sets of data in this table. The one on the left is the most interesting. That's the overall timings, and then also broken down separately into the timings for 2 electron integrals and also for the exchange correlation quadrature. And I've highlighted the numbers in blue because that's what I want to focus on today. Those are the parallel speedups for the new OpenMP code. Scaling on a single node that contains 32 cores, and then you can see that for the overall timings, we get a speedup of about a factor of 12 running on all 32 cores. And then if you just glance over the MPI numbers from the old version of Q-Chem, you can see that the parallelization tops out at a speedup of about a factor of 5. And so in the last row of this table in orange, I have computed the ratio of the MPI time to the OpenMP time running on all 32 cores, so running on one compute node. And so the punchline, the most important number to take from this table, is that we have a factor of 7.4 speed up over the previous MPI-based parallel code when running on 32 processors. So running on one compute node, your time to solution is enhanced by a factor of 7.4 relative to Q-Chem 5.0. That's maybe a little more digestible in this graph, which is the speed up factor versus the number of cores. And so the scaling in neither case is ideal, at least beyond about 6 or so processor cores, but you see that the old MPI code really asymptotes at not much more than about 10 or 12 processors. You're still getting some enhancement all the way out at 32 cores with the multi-threaded code. We didn't have any 64 core nodes lying around, but I'd be interested to see some timing benchmarks on those if anyone wants to dabble on their own. So anyway, we get much better parallel speed up with the new OpenMP code. And then let me show you one more dense eye chart of data to demonstrate that this is not unique to the one functional that I chose in the previous example. So for that same molecule, now just looking at the overall time for the whole frequency calculation with either the omega B97XV, those are the data that I showed you on the previous slide, that's a range separated hybrid, or with B3LYP, obviously it's a widely used global hybrid, or with PBE, which is a pure GGA, does not contain Hartree-Fock exchange, and so the timings are faster overall. But you can see that the parallel speedups that we're getting are roughly the same for all three functionals. So scaling up from 1 to 32 cores, we see a parallel speedup of something like a factor of 11 or 12. And then again, in the last row of this table, plot the ratio of the time on the new code versus the old MPI-based parallel. And again, you're getting speedups of factors of 5, 6, 7 relative to what you could have been running with Q-Chem a year ago. All right. So I'm going to show you sort of some of the same type of data now for RIMP2 gradient, namely new multi-threaded parallelism. So first of all, just as a brief technical note or item of interest, this is really, this RIMP2 gradient implementation that I'm about to discuss is really the first production level deployment of what we've been calling internally libQints, and that is a complete from scratch rewrite of Q-Chem's integrals code. It's designed to be much more flexible and in particular much more scalable in parallel, and that's what I'm going to show you right now. So there will be a lot more to come with libQints in future releases. But for right now, libQints is turned on as the default for RIMP2 gradients. Well, we'll be starting with Q-Chem 5.1. So if you're not familiar, this is the resolution of identity approximation to MP2, and that approximation is good to 60 microhartrees per atom is a number that people throw around. However, energy differences relative to full canonical MP2, there is essentially no difference. So I would actually argue that we could turn on resolution of identity as the default for MP2 calculations, as some other codes do. Certain prominent members of the Q-Chem developer community are opposed to that philosophically, thinking that if we call something MP2, it had better well be exactly MP2. I guess I take the point of view that if something looks like a duck and quacks like a duck and predicts the same relative energies as a duck, well, see where I'm going with this. But anyway, so this is RIMP2 gradient. I'll show you data for 3 different molecules, ranging up to about 700 basis functions at a double zeta level of theory. And the data that I'm going to show you are parallel speedups. So this is running either in red with what will be the default algorithm starting with Q-Chem 5.1, and that's the libQints based algorithm, versus the red data are the default algorithm in previous versions of Q-Chem, and that's with the old integrals code. And obviously you can see that the scaling is much better with the new code. And in fact, on this same 32 core node, this speed up is pretty close to ideal out to 16 cores, and not that far off of ideal even at 32 cores. Now, libQints is a work in progress, and at present, the old integrals code is still faster on one processor than the new integrals code, and what that means, but the new integrals code scales much better, which is what we're seeing here. So that means that somewhere there's a crossover where the actual time to solution with the new code becomes faster on a certain number of processor cores. And those are the data shown in the graph at bottom right. It's showing you that the break-even point in terms of time to solution is at about 4 processor cores for all 3 of these molecules. And so if you have available any more than 4 cores, then you're better off running the 5.1 default algorithm using libQints. And these days, most of the time, people do have access to a lot more than 4 processor cores, and so that's why we switched the default. But the old algorithm is still available in there, should you be running in serial. So anyway, so much better scaling for RIMP2 single points and gradients. The gradients is a harder calculation, so that's what we show here. And so better scaling means better time to solution if you can run it across a whole node. Okay, so I guess there's one more slide here, which was just to show you some inputs. So I'll just show you right here for new code and for old code. So as I said, the new algorithm is the default, so there's nothing special to specify there, except to note that the new algorithm can really take advantage of large memory. And again, it's not too unusual these days to have something like 32 cores and 120 gigabytes on a node, and that's what we had here. And so you see that mem total is set to 120 gigabytes for the calculation on the left, which uses the new code. In the old code, it's not set up to exploit that much memory, so you really don't need that much memory. Actually, it's limited by Fortran memory, probably to 2 gigabytes. But anyway, should you want to run the new code, you simply set use, or to run the old code rather, you simply set use libQints equal to false, and you get the previous 5.0 version of the RIMP2 gradient algorithm. Okay, so moving onward to brand new features, let's talk about CASSCF. So if you're familiar at all with CASSCF, complete active space self-consistent field theory, you know that this is basically Hartree-Fock theory for static correlation. So it's a mean field theory. There's no or very little dynamical correlation, but it's full CI in an active space. And so you do get all of the static correlation associated with your active space orbitals. And so in cases like bond breaking transition metals in the ground state, or some people would argue anytime you're in the excited state, you have significant multi-determinant character. So you might want CASSCF. So CASSCF partitions orbitals into inactive, active, and virtual. The inactive ones stay doubly occupied, and the virtual ones stay empty. And then in the active space, you have a certain number of orbitals and a certain number of electrons, and you do full CI in that active space. And then depending on whether you want to do orbital optimization or not, you get either a CAS-SCF calculation or a CAS-CI calculation. And in either case, like any full CI calculation, the cost scales factorially. The number of determinants that you can create scales factorially with both the number of orbitals and the number of electrons. And so conventionally, people talk about the limits of CAS-SCF being, depending on what code you're running and your level of patience, something like 14 electrons in 14 orbitals out maybe to 16 electrons in 16 orbitals on a good week with a lot of patience. The developer of this, who by the way is Daniel Levine in Martin Head-Gordy's group, says that CAS 1515 should be feasible with the present version of Q-Chem's CAS-SCF code. So that's 15 electrons in 15 orbitals. But better yet is a new algorithm called adaptive sampling CI. And so this is an approximation to CAS-SCF, but it's designed to be an a priori version or a black box version of CAS-SCF, where you don't need to select an active space, where you iteratively define and then refine an active space in order to achieve a user specified tolerance. So there's one input parameter that then ultimately defines the active space in an automated way. So how do we do that? We do that with the criterion that you see here. Knowing the CI coefficient Cj, we can evaluate this this quantity that's shown in orange to get an estimate, which based on your current knowledge of the energy E, to get an estimate of the coefficient Ci. And then the idea is that if Ci is sufficiently large according to this estimate, then you throw orbital I into the active space, or I guess probably these are coefficients for determinants. So throw determinant I into the active space, and then iteratively improve that, including more and more orbitals in your active space until you achieve a user specified level of accuracy. Those determinants get treated in the usual CAS way via full CI, and then all of the other remaining small coefficients get treated with perturbation theory. And so the idea here is that one can scale up to much larger active spaces, but also active spaces that would be achievable can be achieved faster. So just in a fairly small test calculation, CAS 1010 with the current version of Q-Chem's code took 30 seconds, but for the same molecule, we can go all the way out to a CAS 1418. And now I told you that would break most existing exact CAS-SCF codes, but in fact, we do it in less time than the CAS 1010. And the developer assures me that active space on the order of 50 electrons in 50 orbitals should be feasible with this adaptive sampling CI code. And now here's a long list of rem variables that you need to control these calculations, which you can either commit to memory quickly or you can look up in the manual later. And I will move on to talk about magnetic parameters, or parameters for EPR Hamiltonians. And this is work that comes from Daniel Lambrecht's group at the University of Pittsburgh, and Eric Bergquist in particular is the student that did the work. And so there's two different features here that both fall under the general rubric of spin Hamiltonians. So the first are hyperfine interactions, and so this is the interaction between an electron spin and a proton spin, or rather a nuclear spin. So interaction between an electron spin and a nuclear spin is shown in the little diagram here. And then in this energy level diagram, it shows you that the spin orbit coupling gives you your fine structure. So that's where your your doublet P splits into its two spin orbit components, J equals 1/2 and J equals 3/2, and then the spin-spin interactions come along and put the hyperfine structure on top of that. So the Hamiltonian for that hyperfine interaction you can write as a coupling matrix A, and then take its inner product with the spin angular momentum of the electron S and the spin angular momentum of the nucleus I. And that coupling matrix consists of an isotropic part that's usually called the Fermi contact interaction. It depends on the electron density at the nucleus. And then a dipole-dipole part, a spin dipole part. So both of those are implemented in Q-Chem. So you run this calculation, and what you get back is the coupling matrix A decomposed into its isotropic Fermi contact part, and then also the spin dipole coupling matrix. The other feature implemented by the Lambert group that I've put here under spin Hamiltonians are nuclear electric quadrupole interactions. So if your nucleus has a quadrupole moment, then it can interact with an electric field gradient. And again, there's a coupling tensor that dictates that interaction. And so this has been implemented at the SCF level, both Hartree-Fock and density functional theory. So you set up your usual REMs for a Hartree-Fock or a density functional job. As I haven't shown it here, but you can look up in the manual later that the additional REM variable that you need is magnet equal to true in your $rem section. And then there's a $magnet section that will define, that will set up the fine structure calculation. And so this slide that I'm showing you here is a snippet of the output from the spin dipole part. So you see the isotropic Fermi contact interaction in megahertz, and then the spin dipole contribution. So that's the anisotropic part of that A matrix, that coupling matrix. So this comes out with the same setup, magnet equals true, and this $magnet section. You also get these nuclear electric quadrupole interactions. And so you see here, this is the raw electric field gradient tensor. So that's the coupling matrix that you need. And so again, you get both of these things by setting magnet equal to true. All right, buzzing right along. The last itemized feature on my list is CVS-EOM. So CVS is Core-Valence Separation. So this is a very old idea for calculating core excitations. The problem with calculating core-to-valence excitations, if you do them naively, is that you would need to calculate an intractable number of excited states to iteratively work your way up from the lowest state all the way to core excitations at tens or hundreds of electron volts. But the energetic separation between core and valence orbitals is significant, and so those really don't couple in these core-to-valence excitations. And so largely you can neglect the valence occupied orbitals, just consider the valence virtuals, because that's where your electron is going, and the core occupied. So I've always thought that frozen valence would be a better term than core-valence separation, but CVS is pretty standard terminology. Let's see. So I think these are the things that I just said. You're going to freeze some core electrons in your reference CCSD calculations, and those are then going to be the core orbitals that form the occupieds for your occupied to valence excitation, and all of the orbitals that were iteratively optimized in your CCSD calculation are going to be frozen. So job control, set up your core-valence separation, EE as in the electron excitation version of EOM-CCSD theory, and then some frozen core orbitals that will get discussed on the next slide. So I guess they'll get discussed in one more slide. This is a way to calculate X-ray spectra, and in particular, NEXAFS spectra, or near-edge X-ray fine structure spectra. So here are some experimental data for the carbon monoxide molecule, and there's a K edge for both elements, carbon and hydrogen. So excitation energies that you can read there. And then we run this CVS-EOM calculation with a decent basis set, and the carbon energies come out basically spot on. So actually the pi star is exactly equal to the experimental value, and the 3s3p excitation differs from experimental only by about 0.3 electron volts. And then also very accurate excitations for the oxygen edge that are sort of intermediate between these two sets of experimental numbers that are in this paper from 1989. So very, very good accuracy. And then just one more technical note about how to set these up. So Q-Chem in all equation motion couple cluster calculations wants to calculate the lowest excited states for a given irrep, given irreducible representation. So you iteratively work your way up, starting from the lowest excitation for a given irrep. So what we're going to do here in these CVS calculations is freeze the valence orbitals. So you're still going to calculate the lowest excited state for a given irrep. It's just that you're going to make that lowest excited state a core-to-valence excitation by not allowing excitations out of any of the valence occupied orbitals. And that means that if you want to calculate the oxygen edge of this CO NEXAFS spectrum, the oxygen core orbitals are of course lower than the carbon core orbitals because the atomic number is larger. And so in that case, you want to freeze one core orbital so that your next, you want to freeze one core orbital because then your carbon core orbital is frozen and you're getting excitations out of the oxygen 1s. Whereas if you want to calculate the carbon edge, you want to freeze two core orbitals so that you're getting excitations out of the carbon 1s orbital. Okay, and then the last couple of things are somewhat more specialized. I think all 5 things that I've just discussed are probably of interest to a broad swath of the quantum chemistry community. The last 2 things are a little more specialized, but I'm going to take my prerogative as person who put the webinar together to tell you about 2 new features that come from my own research group that I'm quite excited about. And the first of these is so-called Poisson boundary conditions for quantum chemistry calculations. So my group's been working on continuum dielectric solvation models for quite a while now, but recently we've become interested in looking at solvation at the air-water interface, and there you cannot use a standard polarizable continuum model because the solvent environment is not isotropic, right? You've got water sitting below. This is a picture from the hydrated electron, which is another thing we've worked on for a long time. You've got dielectric equals 78 below in the water part, and you've got dielectric of 1 in the air part. And so what we'd like is a continuum solvation model based on a dielectric function rather than a dielectric constant, so that we can cook something up that transitions from epsilon equals 78 in the water part to epsilon equals 1 in the air part. And then we're just going to solve Poisson's equation using that spatially varying dielectric function. And so we have what we call a Poisson equation solver. It works at any level of theory, although you're going to use the SCF density to polarize the continuum. And then we have non-equilibrium formulation for calculating vertical ionization energies that considers the fast electronic response of the solvent upon ionization in the same way that we implemented non-equilibrium PCMs, both for vertical ionization and also vertical excitation some time ago. And then we've used this to perform what I think is to date the most accurate calculation of the vertical ionization energy of the hydrated electron. You see that if we just try to use a PCM, this is actually in bulk water, but the other thing that these Poisson boundary conditions have going for them is that they treat exactly the parts of the wave function that may penetrate out of your solute cavity that you would construct in a PCM calculation. And so that PCM calculation, even in bulk water for this species, exhibits an error of about half an EV in the vertical ionization energy. And with the Poisson equation solver, we basically nail it in bulk solution, but we can also calculate it with a different dielectric function at the air-water interface. And then the second thing is an Exciton model, and this was actually the PhD thesis work of our moderator, Adrian Morrison. So I had a couple of experimental colleagues at Ohio State that came to me with this nanotube system that's shown at the left, and wanted me to do some calculations on that. And so we originally did calculations on this 9 chromophore model that's shown at the bottom, and you can see that those are pretty delocalized, and to do TDFT calculations on that was taxing. It's doable, but it's taxing. And so what Adrian built is a modern version of a very old idea, Frenkel-Davidov Exciton model, where we're going to expand our excited state wave functions for the collective system, for this collection of multiple chromophores, as direct products of excitations that are localized on individual chromophores. And the advantage of that is that we can calculate those independently, distribute them across processors. And then I said this is a modern version of Frenkel-Davidov, and that's because we don't make any of the sort of crude approximations that had to be made back in the day. In particular, there's no dipole coupling approximation for the matrix elements, and so that dipole coupling matrix, or that dipole coupling approximation, is probably reasonable if your chromophores are well separated, but maybe not if they're closely packed, as in a crystal or in this nanotube. And so we, in fact, the approximation that we make is this ansatz, expanding as direct products, but then we calculate exact matrix elements of the Hamiltonian, and we diagonalize that fairly modest exciton Hamiltonian to get our excitations. All that was available in some previous version of Q-Chem. So what is new in 5.1 is that we have derivative couplings for this model. So those are these quantities HABX, where X is the nuclear coordinate, and that's showing you how the matrix elements of your exciton Hamiltonian change as a function of the nuclear, of the vibrational coordinates. And so those parameters, HABX, are the things that in the solid state physics literature get called either Holstein or Pierrelis couplings, exciton phonon couplings. So the diagonal ones get called the Holstein couplings. So that's telling you how the so-called site energies, the energies of the individual chromophores change as you perturb the nuclei. And the Pierrelis couplings, the off-diagonal ones, are telling you how the energy transfer couplings change as a function of nuclear coordinates. And then Adrian wrote a couple of papers applying this to study singlet fission in crystalline tetracene and trying to understand the mechanism that makes singlet fission go in tetracene, even though it's ostensibly endothermic. And by means of these derivative couplings, what we're able to identify are important vibrational modes that strongly couple the two excited states that are relevant in singlet fission. I won't tell you about those states, but we can identify them. And we also learn from this that the Holstein couplings are really the only ones that are significant. There's a factor of about 5 orders of magnitude difference in the scales of these two figures. So it's mainly the modulation of the site energies rather than the energy transfer couplings that's driving this process. And then you can see at the right a picture of one of the vibrational modes that we were able to identify. So a key feature of this is that we can use these derivative couplings to identify what are the important vibrational modes that couple strongly to energy transfer in this exciton model. So that's it for my group's work, and just a few other things that fall under etc. We have a couple of other performance improvements for a couple cluster methods, a little bit better performance when the reference is unrestricted, and a little bit better performance for the EOM-CCSD gradient. Some new things for resonances within couple cluster theory. So Thomas Jagow in Munich has implemented gradients for the so-called CAP-EOM-CCSD. So this is EOM-CCSD with a complex absorbing potential to study resonances or excitations that lie above the ionization threshold. And then Anna Krylov has implemented natural transition orbitals for trying to visualize and understand the orbital character of those resonances. And then some new things for energy decomposition analysis. So the ALMO energy decomposition analysis method that's been under development in the Head-Gordon group for quite a while now has in Q-Chem 5.1 been extended to excited states that are treated with either CI singles or time-dependent DFT. And then an alternative EDA that my group reported a couple of years ago based on a combination of symmetry-adapted perturbation theory and constrained DFT is also available in 5.1. And so finally, let me go through the list of all of the people who have contributed. So at the risk of sitting here and reading you this slide, I'm going to sit here and read you this slide because I think that one of the great strengths of Q-Chem is the fact that we have such a large and diverse group of developers, and that really lets us do a lot of really innovative things. So Yuzi Mao is the person in Martin Head-Gordon's group who's been working with the ALMO EDA recently and implemented ALMO EDA for excited states. I mentioned Thomas Jagow in Munich with the complex absorbing potentials. I also mentioned Daniel Levine for CASSCF and the adaptive sampling CI. Ilya Kalaman, who actually just started as our newest Q-Chem employee, has done some work with improving the performance of CCSD. Zhentian Feng, who also works for us, has implemented the Core-Valence Separation. I told you about Adrian's work on the exciton model. Evgeny has been working on libQents and is finally ready to roll it out. I mentioned Eric Bergquist and Daniel Lambrecht for their EPR Hamiltonians, Anna's natural transition orbitals for resonances. Zhentian Gan has really done a lot with basically has done all of the OpenMP multi-threading of our integrals code. So both for DFT energies, gradients, and now finally for Hessians. Mark Koons in my group did the Poisson equation solver, and then Ka-Un Lau, who got his PhD with me a few years ago, did the SAP DFT energy decomposition analysis. And so that is all that I had. And so I think Adrian is going to take over and moderate the questions.
Thank you, John. It's a really interesting presentation. Lots of really cool new stuff in 5.1. I'm excited for it to get in the hands of Q-Chem users. We have one question here from the audience. Feel free to send more. And John, feel free to punt these back to headquarters if you'd like. But the audience member asks, does the new libQN's integral engine allow for RIMP2 with ECPs?
I would definitely punt on that one.
And punt received. They absolutely will support RIMP2 with ECP basis. Let's see, on the subject of RMP2. John, could you comment on the scaling of RMP2 relative to exact MP2, and maybe your experience with the type of systems we might be able to handle with that method?
Yeah, so formally the scaling is the same. It's fifth order. Actually, if you really dig deeply, the formal scaling is slightly worse because one of your n's in n to the 5 is the size of the auxiliary basis. But in practice, it turns out to be a win because you never get to that limit. And so in practice, it's n to the 5, but with a significantly smaller prefactor than canonical NP2. And the number that we used to throw around in Martin Head Gordon's group when this was under development was a factor of 20. That's based on my 15-year-old recollection, so take that for what it's worth. But it's n to the 5 with a significantly reduced prefactor. And so the examples that I was showing were things with on the order of what was it? No more than 700 basis functions, but those were for optimizations. So that's certainly feasible. If all you want to do are single point energy calculations, you can go much, much larger than that easily. I know for sure that we've done single point RIMP2 with in excess of 3,000 basis functions, maybe 3,500 basis functions, and that's probably not the absolute upper limit either. For geometry optimizations, of course, it's more expensive. You've got however many optimization steps plus a gradient, but certainly molecules of the size that were in my test examples and things a bit larger than that should be feasible.
Great. Yeah, it's impressive. We got a few more questions from the audience, and I think maybe this one is a excuse to give a brief overview of the SAP CDFT method. This audience member is asking about the charge transfer term in SAP, and if there is a possible alternative to, or similar theory to SAP as an explicit CT term.
What was the last part?
Is it possible to create an alternative theory or similar theory to SAP with an explicit CT term?
So that's actually exactly what is this audience member a plant? I don't know. That actually is exactly what we did. So I don't have the picture. Look what I can do here. I do have the picture. So here's the picture. It's in this table of contents graphic. So the basic problem with the old definition of let's just look at this part is what I want to look at. The basic problem with the original Stone and Mesquita definition of charge transfer in symmetry adapted perturbation theory is that the charge transfer energy goes to 0 in the basis set limit, and they know this, and Alston and Mesquita has actually proposed a completely different way to define charge transfer in SAPs based on regularizing the Coulomb operator. We don't have that in Q-Chem, so I won't discuss it further, but the community has moved on from that old definition because it does go to 0 in the basis set limit, and the reason it goes to 0 and the basic problem is that it's very difficult to define charge transfer in an orbital framework. Now the ALMO-EDA code does this in what seems to be a reasonable way based on these response functions, these FERPs. But the basic problem that they're trying to solve is that in the basis set limit, how do you distinguish between induction, which looks like occupied to virtual excitations on a single monomer, and charge transfer, which obviously is occupied to virtual excitations on between orbitals on different monomers. And in large basis sets, those two things become very convoluted, right? When your orbitals, both occupied and virtual, extend extend everywhere. So the constrained DFT part of the SAP DFT is an attempt to pull out the part of the SAPT induction energy that's actually charge transfer. So when you do a normal SAPT calculation, you get an induction or a polarization energy, and the charge transfer lives in there somehow, because the polarization looks like these occupied to virtual excitations. And the idea in constrained DFT was that we were going to define a reference state that's free of charge transfer, and then use that and do that using constrained DFT, where we're able to constrain the number of electrons on one monomer or the other. Use that to define a charge transfer free reference state, and then use the difference between that and a fully relaxed DFT calculation to define the charge transfer energy, and then simply subtract that number out of the SAPT induction energy and call what remains the actual induction or the actual polarization energy. So without having any material specifically prepared, I hope that gives you a reasonable overview.
Thank you. That answers that pretty well. So we got two more questions here. So this viewer wants to know how the non-orthogonality is handled for AIFDEM calculations, and again, feel free to punt that.
Oh, well, I would hope that I know. I didn't code it, but I wrote down some math. So Adrian coded it and also wrote down the math. But so it's handled by means of a so-called corresponding orbitals transformation. That's a very old thing that allows you to write down a set of generalized Slater-Condon rules. So the Slater-Condon rules that you learn about in Szabo and Osland are valid when all of your orbitals are orthogonal. So these are the rules for evaluating 1 and 2 electron integrals. And so by means of this corresponding orbitals transformation, you can define, you can get generalized Slater-Condon rules that don't require the orbitals to be orthogonal. So that's pretty straightforward. The downside, so the good thing about this is you can distribute those monomer calculations across lots and lots of processors. So you've got essentially a CIS or a TDDFT calculation to do on each monomer, and you need a fairly large number of excited states, or large relative to what you might want in a single molecule CI singles, because you're going to use those excitations as a basis, so you want flexibility. But that part's pretty easy. The downside of the corresponding orbitals transformation is that evaluating those matrix elements, those integrals using Slater-Condon rules, requires something that looks like a Fock build on the entire supersystem. So for each matrix element, you have to do one step that looks like one Fock build for the entire supersystem. However, at some point, Adrian came along and said, well, but actually for the distant monomers, it suffices to use charge embedding. So if you really want to evaluate those exact matrix elements and not make any approximations other than the ansatz for the wave function, then you do have to do a Fock build for the entire supersystem, but only once, not self-consistently, once per matrix element. But we found in one of the papers that Adrian wrote that to a very, very good approximation, you can do charge embedding for all but basically the nearest neighbors And then you're only faced with doing a FOC build for nearest neighbors. So for a small number of monomers, maybe only 2 instead of the whole super system.
That sounds about right.
Is that a pretty good overview of what you did?
Yeah, I agree. Here's one I think that I will take. Customer or viewers asking if we have any plans for MPI OpenMP hybrid algorithms. And that is a good question. I don't have a great answer, but we are certainly considering such approaches. We don't have a definite timeline at this point. But when that becomes necessary or an attractive thing to do, we would pursue that. But again, we don't have anything set in stone with regards to hybrid algorithms.
Yeah, so it is probably still, I should mention that it is probably still the case that if you're really going to the extremely large system limits, where you're really pushing the envelope of what's even possible, that MPI parallel just in general, DFT, MP2, may be a better way to go, just because for very large systems, you should still be able to get scaling with the MPI code beyond 1 node. So you could take it up to more than 32 processors. The scaling, obviously in the examples that I showed, but also more generally, the OpenMP tends to scale much better. And so if you're only doing calculations at the level of 1 node, OpenMP is definitely your best bet. And that's really where most production level quantum chemistry and Gaussian orbital codes lives, is things that you can do reasonably on 32 cores or fewer. And so in those cases, for the vast majority of the everyday work, the OpenMP parallel version of whatever is what you want. But if you're really going to the large system limit, you might look into the MPI version.
Yeah, I would agree with that. We have a question about CAS and ASCII for the large ASCII examples, the 50 electron 50 orbital type calculation. Is that really, the question is that really a CAS-SCF or a CAS-CI?
The answer is I know nothing beyond what's on that slide about that calculation. So I was about to go back to it, but there's no point because I know nothing about that calculation other than what's on that slide. So in terms of the timings, I believe that I was told that those were CAS-SCFs. That proves to be incorrect. Well, you have the disclaimer. But CAS-SCF is implemented, so you can do orbital optimization.
The good news is that Daniel Levine, the developer of this method, is giving our next webinar on the subject of CAS-SCF and ASCII in the next month or 2. So tune back in then for a more detailed answer to that question.
And with an acronym like ASCII, there's got to be a joke there that perhaps Daniel can come up with.
I had a question about Poisson boundary conditions. Are there gradients available for that method? Can we do geometry optimization? Not yet. Is there a plan for that?
Don't hold your breath.
Okay.
The full disclosure, meaning that that's not the next thing that we're going to do with that, because the full disclosure is that method is a little slow, maybe more than a little. So it's an exact solution to Poisson's equation. So unlike PCMs, the advantage of PCMs is that it's only a 2-dimensional discretization. You just have to discretize a cavity surface. And so the discretization is quick and easy. Disadvantage is you don't get an exact treatment of the tails of the wave function. You get an approximate treatment. The Poisson equation gives you an exact, by definition, an exact solution of the continuum electrostatics problem, but requires you to discretize 3-dimensional space. And our first take at that is not blazingly fast. I have a student who's working on it, but that's the next thing that we will do, is just trying to speed it up for single points.
Okay, yeah, that sounds all right. Thank you again, John. It's a really informative talk, and thanks for handling all these questions. Yeah, Q-Chem 5.1, pretty exciting.
Again, I'd like to thank John for giving us this excellent lecture, and also Adrian for great question and answer moderation. I also like to let you know that this will be the last time I host Q-Chem webinar, as I will be leaving Q-Chem next month. I would like to take this opportunity to thank Q-Chem developers and board members who have given lectures in this webinar series, and the Q-Chem users who have participated and supported us through all our webinar series. Especially, I want to thank my former colleague Ihan Shah, who started this webinar with me about 5 years ago, as well as Mary Su, our business manager, who took great effort to make the webinar recordings as videos and upload to the YouTube channel, as well as make it available on Q-Chem website as well. We started this webinar back in 2013, 5 years ago. As I remember, the first webinar was given by Professor Martin Gordon for the wonderful transition state search method, Fusion stream method, which was developed in his group. That was for Q-Chem 4.0. Now we have 5.0, and as John talked about, the latest 5.1 is around the corner in about a week. So please wait for your email notification announcement and give 5.0 a try. It should be a great and robust release. Again, thank everyone for attending this webinar session. This concludes.
And thank you, Jinting, for many years of service to Q-Chem.
Okay, I appreciate it. Yeah. This concludes this webinar session. Goodbye.
This concludes our webinar. We would like to thank John Herbert for his excellent presentation, as well as Dr. Adrian Morrison and Dr. Jinting Gan for organizing, running, and moderating this webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.